All right, let's get started. It's a busy room. Thank you all for coming. Just going to wait a minute to sort of see if the conversation is going to die down. Yes, thank you very much. So I'm Friederike Schuur. I'm a research engineer at the newly formed entity Cloudera Fast Forward Labs. Fast Forward Labs was acquired by Cloudera on September 7th, and I tell you that was quite an interesting journey to be a part of. Just to tell you a little bit about what we do. So we are applied machine learning research group now within Cloudera, and we research new capabilities specifically within machine learning, computer science, statistics, data science that we believe will have an impact on industry within the next 6 months to 2 years. And so compared to a more academic group that makes us, as I like to say, hyper-applied, it also means that there's a certain accountability, because if you make predictions for what's going to happen within the next couple of years, people remember and they tell you if you were wrong. And as a sort of like data scientist, machine learning engineer, I of course like that because it provides me with a signal that I can use to actually adjust my own predictions for the future. One of our most recent research reports that we put out, so these are the products really, we publish little books, we even make them like as actual books. It's kind of archaic, but people still like artifacts, and here you see a picture of one. Should actually start playing. Now you sort of see what it looks like on the inside. So our most recent research deep dive was on model interpretability. And so today I'm going to talk about a topic that comes sort of out of that report, but it's just, of course, a small fraction of it, since this is a much longer book. And really, this one is about Henry VIII, because you all read the title, and this is about why your relationship may last or it may not. And Henry VIII, for me, really is the motivating factor for this talk. He had a lot of different wives, and some found rather tragic ends. Also, like because he didn't want to stay with his first wife, he kicked off the English reform, right? So sort of a new religion came out of that. So it can be pretty dramatic if your relationships are not going to last. We all have our own dramas, I'm sure. So really, why your relationship is going to last or not, that is the question that I'm going to address. And of course, because I can't actually sort of look into the future and say what will happen, I should correct it and say why we predict your relationship is going to last or not. And so this, I think, is likely to last or not. And so this is already actually different from the type of questions that we most commonly ask within data science and machine learning. Often we're trying to predict an event, and then we give these predictions to people either to make more informed decisions or it powers a data product, right? But it is not so often that we necessarily ask, so why did we make that prediction, right? To sort of like ask for the reasons. And that is really what is at the heart of model interpretability, where we're trying to go a little bit deeper into our algorithms to understand what they're actually doing and why they're doing it. And it's a good time to do this now, because effectively we have been too successful. We've developed algorithms that have become incredibly good at making predictions, but they're a lot harder for us now to understand. They're better because they're more complex. It is always sort of there are always two sides to a coin, right? Essentially, what I want to avoid is this kind of future. So does your car have any idea why my car pulled it over, right? And sometimes we're not too far off, right? And if we sort of continue going in this direction, then this might actually at one point become reality, and that's a pretty awkward conversation to have. So to put it sort of in a more serious way, right? So algorithms decide which emails reach your inboxes, whether we are approved for credit, and whom we get the opportunity to date. But as algorithms give answers, they raise questions. If an algorithm denies your loan application, wouldn't you like to know why, or what you could change for a more positive outcome? Or perhaps you'd like to know if the bank is right to trust the algorithm in the first place. These are real questions, right? And some of these algorithms, they are put in place today. And here's another sort of example that I also really care about, right? If we are starting to make these kind of classifications, we better get that right, because this has tremendous consequences for people's lives. And model interpretability is a way of sort of inspecting your model and also gaining more trust in that it is right for the right reasons and wrong for the right reasons. And that's a phrase that will come back. Here we go. We need to know models that we know are right for the right reasons and wrong for the right reasons. And the problem is that sort of the traditional methods that we use, they don't really give us actually that answer, right? So we all know the sort of like standard machine learning workflow where we hold some data aside, we never sort of use them during training, and eventually we sort of test our model performance on that holdout set, right? And then at that point we can see, oh, we're doing really well, this is really great, we have like 95% accuracy. or whichever metric you use in order to do that validation on the holdout set, right? But at that point, really, what you sort of see is, does it do a good job on the data that I've set aside? And while that is important, and you should always do that, and it's really crucial, it doesn't sort of tell you if your model is right for the right reasons or wrong for the right reasons. For example, this is a kind of famous example, actually, in this area where they were sort of looking at the risk of death for people who were admitted to the hospital with pneumonia. And so it basically said that everyone who has asthma has a lower risk of death, right? And now if you base interventions on that, you probably will have a problem, right? And if you now can sort of look in and see, oh, what actually happened here, instead of just looking at the performance of the holdout set, then you realize that they have a lower risk of death because from the very beginning they receive much more intensive care, and that is something that wasn't captured in the original data, right? And so it is about preventing those kind of situations. Something else also, if you know the reasons for a prediction, it might actually also help you to give strategies for what you can do to change the outcome. So here it's risk of an engine failure, 5% is kind of high if it's an airplane, you don't want to be on that. And so if now you know as an engineer what is the one thing that you can do to really drive that risk down, that is a very actionable insight that you can get. But again, it's about why a model makes a certain prediction. I'll come back to this later, there's some risks too. So the benefits of interpretability really is it helps you verify that the model is right for the right reasons and wrong for the right reasons. And so if you know that, then you can develop trust in the model. It also helps you explain model decisions and guide intervention. And then there are two more points that are new, and that is it also helps you satisfy regulatory and ethical concerns. Some of you might have come over from the EU, it's probably a tiny fraction, but GDPR is going to come into effect, and part of that is going to be that EU citizens will have the right to an explanation when a model actually makes a decision about them. It's going to be really interesting to actually see what will qualify as an explanation in this sort of regulatory context. The last point is one that I like to think about sort of outside my work. I think it also will help us to develop a more collaborative relationship with models, right? As sort of more and more AI comes into our life, or machine learning models. I use those terms interchangeably. And this is like a total side note because I don't quite know what AI means when people say AI, right? So read machine learning. But interpretability, it might also allow us to have a more collaborative relationship with models, because really, if there's no way for us to interrogate these models, it becomes really hard to cooperate. It's really like as if you and I want to work together on a project and I ask you questions and you don't give me answers, right? That's a pretty complicated relationship to have, and we're probably not going to get very far. And so interpretability can really help us develop techniques to ask questions to the model and then actually get answers that help us to have a more collaborative relationship. But here's one of the challenges. This is actually why now we need interpretability. It's like more and more complex models have sort of entered our lives, and as they've become more accurate, like here, for example, neural networks all the way on that side, they've also become less interpretable. And that's very natural because neural networks are effectively able, like they're not, I think, fundamentally, philosophically different from a random forest or a linear regression, right? I mean, it is just a type of model that is able to capture more complex relationships between inputs and outputs, right? So we're going away from linear, we can model more interactions, right? Sure, we can automate part of the feature extraction, but fundamentally, we have just designed sort of more complex models that can model more complex relationships at higher dimensions, and so naturally, we are like three-dimensional creatures, and at some point, it's difficult for us to actually follow what these models do. Right? And so that is why as accuracy has gone up, interpretability has gone down. And so here's what we want, right? Setting the goal point. So currently there's an accuracy interpretability trade-off. Accurate models tend to be less interpretable. We want to go into this corner where we don't have that trade-off. And that is where the algorithm comes in that I'm going to talk about today. And I'm going to say it's very, very easy and very simple, actually, and it's really easy to use. And that's great because it means that everyone can use it, right? So that, I think, is a great advantage of doing something that is actually not very complex. So LIME is an algorithm. It's local interpretable model explanation. So that's LIME. And it is a model-agnostic interpretability solution, and that cuts through the interpretability and accuracy trade-off. And it does so by essentially taking a model that's already been trained or that you're training, and you can really take anything. You can take a neural network, you can even form an ensemble out of multiple neural networks if you really want to make it very complicated, though I wouldn't recommend that because it really isn't necessary, but you can. And you take that model and you train it such that it is as accurate as you can get it, and then it's great. And then you take LIME, and that essentially is an algorithm that you can use to then interrogate that model that you've already trained to better understand it. And that is why it's model agnostic. It really is something that you can add on to any other model. And that is particularly great if you have a model that has already been trained, right? Maybe you haven't trained it yourself, and that can make it even harder to sort of understand what it does. And so it essentially also gives you a tool to interrogate maybe your colleagues' works, or even an API that delivers predictions. And I think that's actually particularly interesting. And here's really how it works. And it's actually very intuitive. So the bottom row, the features, that is actually a data point that exists, for example, in your data set. And you want to know for that particular sort of row, often that is a person, let's say this is about churn, you want to know for that particular row, okay, what is the prediction that they're actually going to churn? It's 56%, okay, you get that from the model, that's really great. And then what you do with LIME, essentially you start perturbing all the different features of that person, all the different characteristics of that row, and you see what is the effect on the prediction. So it's almost like you're running an experiment, right? Where you see if I turn this knob, like what's going to happen, if I turn this other knob, like what's going to happen, and you will find the knobs that really have the biggest effect on the prediction. And so essentially LIME is nothing more than a sort of very formalized mechanism for doing that perturbation in a systematic way. Here's a different kind of visual representation, right? So this is a classification task, and I've sort of drawn out the decision surface here. Blue is one class, red is the other class, right? As you can see, this is not an easily separable problem, right? At least like the way how it is represented here. And so we need a model that has a higher complexity than, let's say, a linear model in order to actually sort of capture this one, right? So we're going now in the terrain where we need these kind of models that traditionally are considered to be less interpretable than others. Of course, at the beginning, we don't know what the decision surface looks like, right? So we're sort of starting here. We have one data point. We know the prediction, the label for that data point, and then we start with the perturbation. And so essentially then what we get back as we sort of vary these features is a bunch of yeses and a bunch of nos. And we can then use that in order to fit, just locally, a much simpler model, right, that actually now can sort of separate these two classes. And that is really at the heart of it. That is why it is called LIME, the local interpretable, because essentially what it does, it approximates a very complex decision surface locally with a linear model that is interpretable, and that allows you for that particular row, that particular person that you entered, to actually find out what are the reasons why the decision was made that was being made, where was the churn probability this high, or why did your relationship end? Here's sort of an example. You can essentially run almost anything through it. I get to some of the complications later. But here are sort of two reasons why this is great. So here you see an image, right? It's a Labrador playing a guitar, naturally. And then the image was sort of decomposed into so-called superpixels. So kind of larger areas in the image, right? And then the algorithm essentially now kind of can look at one sort of superpixel and say, okay, what does it contribute here? And this, now you can sort of see that this sort of like upper part of the guitar, it essentially explains actually the wrong prediction that the Labrador is playing an electric guitar. But it kind of makes sense, right? Like it's a reasonable mistake to make. We can now see that it's playing an acoustic guitar based on the body, and then also based on the head of the dog, actually that is in Labrador, right? And that is sort of what LIME gives you. Something else, this is a husky classified as a wolf, so that is a wrong prediction. But what was interesting here is that actually the algorithm that sort of trained this prediction, husky versus wolf, was doing incredibly well on the holdout set. So the algorithm was deemed really amazing, and then just the images, the predictions were shown to people, and people were, yeah, no, these are great, this is really fantastic. And then with LIME, they discovered that it was actually the presence or absence of snow in the background that was actually driving the prediction, whether or not it was a husky and a wolf. And there was because of an artifact essentially in the original data set that was used to train the algorithm. right? These things are difficult to spot, and so sometimes we need tools that can help us in actually identifying some of these mistakes, right? It is, again, about an algorithm's right for the right reasons and wrong for the right reasons. This is a fun one to do. It also works with sentences. You can sort of see what is the contribution of an individual word here to the classification, whether or not a particular article is clickbait or is not clickbait. So you can look at that as well. But let's get back to Henry VIII, right? Because that is really what we were doing. Essentially, what I did in this project, and this was sort of a bit of a side project to really sort of showcase both the upside but also the dangers of some of the model interpretability solutions. And at the end, I get to this. But I chose this data set, which is actually a really rich and interesting data set. It's on how couples meet and stay together. And it's a longitudinal study where people were asked over time whether or not they were still with their current partner, and they recorded a lot of different things about these people. It was originally actually sort of collected in order to sort of study the effects on dating behavior in the sort of age of online dating. So there's lots of really interesting stuff in there. But that's sort of aside. I chose it because this is a data set that most of us, I believe, have fairly good intuition for, right? We all have like sort of our own experience of establishing relationships and probably some painful breakups. So that means that we can use our own intuition in order to then actually interact with the data set and also with the results that Lime returns. And now I'm going to show just some sort of screenshots from an IPython notebook. This is all actually online. If you guys want to play with that, like, please do go to that link after the talk. I think people that actually do this sort of live demo are very brave, and I took the screenshots instead. But essentially, you can like install Lime like in any sort of, it's a very easy install, pip, whatever you want to do. It's easy sort of to install for Python users. And then really, like, you need to basically instantiate the Lime tabular explainer object, and you need to give it a few things. It's actually all relatively straightforward. You need to give it just some data. Here I gave it just my training data set. And that is because it wants to know some of the distribution of the different sort of features and variables. Then you need to give it essentially the sort of labels of the classes that you are predicting. You also need to tell it what are my categorical features, what are my continuous features, and then also for the categorical ones, what are the names of all the different levels. So that is fair that it needs to know that, and relatively straightforward to give. So you do that at the beginning, and then once you have instantiated, you already have a trained model, then essentially you say, I want to now look at an example, for example, example 3. And then really you take the object that you have instantiated, you feed in the sample, and then also the pipeline predict probability. That is essentially sort of my model object that gives me back a probability. And that is also one that Lime uses under the hood. And then here, really, this is what comes raw out of Lime, so there's nothing else that I needed to do in order to sort of generate that, except for the code that you saw above. And for this particular one, you see that there's a probability of staying together of 92%. And now you see the 5 sort of factors that either positively or negatively contribute to that sort of very local explanation for that particular data point. And in this case, the reason why the probability is quite high is because they're already married. That's actually something that typically has a very high, kind of really contributes to a high probability. You also can see that like some college is sort of negative, a young age actually is negative. And if you own property, that's good for your relationship. So get on it. But let's take a little bit of a closer look, because really Lime is very, very easy to use. There's only one complication, and that really has to do with like the line that I have in here of pipeline.predict proper. So essentially my sort of model object. Because one of the challenges really is that Lime returns an explanation in terms of the features that you sort of put in, right? And that's really great if you have a continuous feature that is like literally age, right? Then it tells you, it sort of does discretize it into bins, but it then returns sort of like under 32 or between like 32 and 38. And that is again, like Lime talks to you in a language that you can understand, right? The challenge sort of comes if you were to now use, for example, you do natural language processing and you use word embeddings, right, instead of a bag of words approach. Well, to get like the dimensions of a word embedding are not interpretable. Like, and people try, and it seems there might be sometimes, but they're not interpretable. And so, of course, if you sort of give it like all the data in terms of like word embeddings, then at that point it will return to you the dimensions of a word embedding. that are being deemed important, and then you are really none the wiser, right? Another example is if you use an image and you feed it in and then it returns like which pixel is important. Again, that is sort of like something that like if we look at it, that's not really going to be helpful. And so we need to construct it in a way, we need to feed in the features in a way that they're not necessarily the features that are best suited for building a model that is highly predictive. We need to feed it in a way that we can understand them. That means that we need to essentially wrap up our entire pipeline, right, that it is part of the model object. And that can sometimes be a little bit tricky. And so that is where, honestly, I spent most of my time. It wasn't really so much around sort of using Lime. So it means how nice Lime is. It's some of the other things. For this one, it's relatively easy. And you can really use like the sort of scikit-learn has really awesome pipeline constructor, so you can use it here. This was really for my specific problem. Again, the IPython notebook, you can sort of see the entire pipeline that I built out, so that is good. It's just sort of the heads up for where actually the sort of complication lies of this. And then you set up your model. Here it's with a little bit of grid search. I just used the random forest classifier because for these purposes it really doesn't matter like which model I sort of use. Random forest, it is not a linear model. It is not easily interpretable. It is of course not sort of, doesn't have the same like complexity as a neural network, but it is already one where I think using this technique can really be helpful in trying to sort of understand it. You see at the end there's pipeline fit, and then of course that is then also what I feed into Lime. So here we see this again, the pipeline predict probability. So that's really all that there's to it. And that's nice, right? Because, I mean, essentially interpretability, like there's sort of certain steps that by convention are part of the machine learning pipeline, right? Things that we do, like we sort of split our data, train and test, and things like that, right? And so the fact that this is really easy means that essentially you can use it to extend any machine learning pipeline, and that really is a good thing to do if you sort of want to get a better handle on what your model is doing and why it's doing that. Just briefly to look at a bit more of the output, of course, from the random forest, I can get sort of feature importances, right? And that is something very different from what Lime actually returns. And that's sort of important to really understand, like, why do we need to worry about, or why should we be using Lime, right? Feature importances, that is what is important for the model at a sort of global level, right? Like, what are the variables really that, and in terms of random forest, that it sort of splits on early on. So that is like, what is important for the decisions across all the people or all the rows that you've got in your data set, all the data points, right? And here you can see that age and partner age, and actually the difference also in age between the partners is something that is deemed to be very important at a global level for the prediction. But then if we sort of go back to the original example, the age here only shows up in 3 and 5, and the age difference doesn't even make it into the top 5. And here you can see that really the feature important, like random forest has built a model that sort of doesn't just capture sort of like linear surface, it does capture some of the non-linearity. And so now if we use Lime to sort of build these local linear models for the explanation, we do sort of see other factors that come out of it. To show something else, to really show that it can really differ based on what data point you put in. For this particular couple, they have a lower probability of staying together. It's still not bad, 0.69. But here it is essentially the highest contributor to sort of what drives the probability up is the fact that they own the house. So that's really great that they're just living with their partner sort of brings it down. And here what we also see is that the sort of a lower education level, according to Lime, also decreases it, while a higher age, again, sort of increases the chance of staying together. This is why I did this in the first place, this project, of course, right? Like, can we do this? And so let's go through it, right? So, fictional couple, maybe model of the real ones. They currently have a chance of staying together 0.73%, right? And so here, the biggest contributor actually for the sort of, for that chance is that the partner has an education of bachelor's degree or higher. Not married, live in New York, so no owning property. Also, what's interesting is political Democrat. Democrat actually lowers your chances as a couple of staying together. But hey, I know, right? Hey, I just got a raise. This is great. So I put this in. Didn't really change much, so, you know, sometimes that doesn't really help. But, of course, what if we bought the apartment, right? Then at that point, what was really high here as sort of like, so we can see the first one was education was sort of a positive contributing factor living together and renting was negative. With the raise, we now see that renting actually now is in second. It's still negative contribution. If we buy the apartment, of course, that changes. So it drops out essentially of the top 5. And now we can see education is still up. And now it is living together. And so we really just should get married. And then all of a sudden the world looks entirely different. So, it's probably not the best idea to now go on Tinder and then marry the first person that you encounter and hope that you're going to be happily forever after, right? And then this is why I use this data set, where like it is immediately obvious why that may not be a good idea. But if you use this on other data sets where you don't have the best intuition, actually, some of this might lead to problems, right? And this is a given, but I think it's still often an important point to make, where like data are always traces of past activity, right? And so behavioral data encode past behavioral patterns, some of which reflect outdated conventions, prejudice, or even harmful past practices. And that is why I think it is interesting that actually here political democrats sort of shows up here, right? They're sort of like norms, of course, that are captured in the data because we've recorded them coming from people that like were alive in the world like as of 2 years ago, I think, which is when the data collection ended, right? And so these are, of course, not causal factors, right? And yes, it is sort of obvious to us that just getting married doesn't mean that you're going to be happy together, right? But when it comes to other data sets, like, for example, churn data sets where, or the engine data set that I mentioned earlier, right? Yes, we are sort of running an experiment on the data set by doing the perturbations using Lime. And typically in the world, we're establishing causality also often by running experiments. But of course, these are just experiments at the level of data, and not actually at the level of sort of real-world intervention. And so while the outcomes of Lime are very informative and are very useful, especially for understanding whether or not your model is right for the right reasons and wrong for the right reasons, it doesn't, of course, actually give you a guide for like what causes what, right? And that is still something that then requires sort of a bit of common sense judgment. And here's really why I also talk about this, and this is from a ProPublica study. I'm sure some of you have read this, but this is sort of a model that's being used in order to predict the probability of committing a second crime. And so here on the left, you sort of see 2 people that were arrested once. For Brisha, it was actually really just like seeing like a kid's bicycle unlocked and thinking it would be fun to just ride on it. And then she was sort of like said, you stole the bicycle, and she was, And you can see that like the algorithm deems her as high risk versus the other guy. It's low risk, apparently. And then if you actually look at what happened afterwards, Risha didn't commit any other subsequent offenses. Vernon actually did. And so probably the score was driven by something else. And that is really why we need more ways of interrogating the machine learning solutions that we built in order to capture this early. Because I do believe that most of us, like working in this field, we have the best intentions, but it can sometimes be very, very difficult to spot when we're doing something that actually may not align with our own best intentions. So to wrap it up, the benefits of interpretability are really to verify the model is right for the right reasons and wrong for the right reasons, and to develop trust in the model. It can explain individual model decisions and guide intervention, but of course there's still the human judgment piece. It can satisfy regulators and ethical concerns and develop a more collaborative relationship with models. The benefits is the model-agnostic interpretability solutions like Lime avoid the interpretability accuracy trade-off. It works with any model, even the ones that are already trained, even APIs. Lime is easy to understand, very easy to use, and it can extend any machine learning pipeline. Just a bit of a heads up, Lime works best with tabular data, so both continuous and categorical. For text, it just sort of like randomly deletes words and puts them back in. It's not the smartest strategy, though it does give you some intuition. For images, the hardest is actually to construct the features that you can feed into the model in order to make it interpretable, because really choosing the right superpixels is not a trivial task at all. And I wanted to include this because this is a bunch of other resources that sort of are related to this topic. So on top, there's a blog post that I wrote about this talk, and then also the IPython notebook that you can go to if you want to sort of play with it yourself. The original Lime paper and also the code for that if you want to look at the implementation. And then there are a bunch of other like really interesting approaches to interpretability, and I can't sort of all fit them in a short talk. One is interpretability via influence functions. So here what you look at is actually which data points in my training set were particularly responsible for getting the trained model that I have today, which is a really interesting one. Attention layers in neural networks are also a way of actually seeing what, when neural networks sort of process the data, they're actually paying attention to in the data. So that's also a really interesting and different approach. And feature visualization, it just came out of, was just published in Distill, like a really good publication that tries to communicate machine learning results in a easy to understand language, which I really appreciate. That just had a really nice blog post on feature visualization, especially of like neural networks sort of layers and the activations in it. Great, thank you. Yeah, do we have microphones? Should I just, no? Okay.
I'll just shout.
Great.
So, for couples, people tend to be with other people their age. And so if you're varying each person's age independently, ignore the natural correlation between them. Does Lime account for this?
I mean, Lime treats all the different features that it sort of takes in as independent and then varies them independently, right? Like in this case, it's sort of, and that does simplify things, right? Because I mean, the derived feature, the age difference, right? Like it is dependent, of course, on the ages, and it's not smart enough to also then sort of like adjust that accordingly, right? So these are some of the shortcomings. It is definitely something that sort of tries to simplify a more complex reality in order to recover the interpretability. Yeah. Yeah, so first of all, the unit, the way how you should read those is actually just kind of relative to one another. So if one bar is twice as long as another one, it is twice as important. Otherwise, as units, they don't have a like straightforward interpretation in that way. So it is really about the relative importance of the different features to each other. It is ultimately because it fits under the hood like a simple sort of sparse linear model. It is related to the weights in those linear models, right? But the relative, that is sort of how you best interpret it. When it comes to the second part of your question, remind me again. It's always so hard. Oh, now I remember. Yes, the way how that changes. Yeah, I'll go back to like another slide that's relevant here, and that's, sorry, it's a few back. That's really this one, right? And really what we're after, there is some sort of like complex decision surface, right? And we're interested in understanding that. And so we only look at these sort of local patches, right? And in these local patches, there are different variables that then at that point matter the most for the given prediction. Right, and so if you just look at sort of, as I did, like in a sort of narrative, changing one variable, see what happens, like it is not that like the sort of thing on, you change something, like as you sort of saw, you change something and then the whole order sort of changes, because you're essentially in this decision surface, like in a different spot, right? Because a lot of them, there's sort of like multi-dimensional spaces that you live in, right? So you're essentially in a different spot, and so it is not really like, when you just look at 2 or 3 examples, like intuitive actually how that relates back to the decision surface. But Lime also, as part of this algorithm, has a way where you can strategically pick data points that are the most similar from one another, that essentially that helps you in a more efficient way, like map out what this more complex decision surface actually looks like. And then at that point, like the intuition that you're after, right, that then is the one that you can actually it's easier to develop then at that point, because then you're choosing the examples really, basically if we sort of look at this, right, there's sort of some, like in the entire sort of square, there are some points that would be more interesting for a sample data point to explore what is the explanation for the data point, right? They're typically the ones like close to boundaries, but at a different location from the one that you've already looked at, right? And so Lime has an algorithm that allows you to like strategically pick those and then sort of see what is important at those locations, and that can help you to develop the intuition that you want, that you're essentially asking for with your question. Yeah, that's great. So what I was doing in my talk is like there was one couple, and I was changing some of the features, kind of like, hey, I got a raise, hey, we bought a house, in order to see what happens, right? What Lime would be doing in this algorithm, like sort of part 2 of what I presented today, then you pick the different couples in order to strategically explore that space, right? So distinct from what I was doing. And that strategy is much more suited to actually then slowly developing and understanding what that decision surface actually looks like, right? Partial dependence plots, it is a sort of related idea, right? Because essentially what you're doing here, you're sort of plotting data in a way that you can explore interactions between variables in your data set, right? But here, because visually we can't process that many dimensions, it's typically limited to 2 or 3 or something of that sort, right? And so that is not enough. And then also with partial dependence plots, we have to actually decide what we're going to put in, right? So we need to use our prior sort of intuition for what might matter. And so I think actually using Lime in combination with partial dependence plots to actually guide the decision for what you want to put into partial dependence plots to have a closer look at could be really fruitful. So this makes me feel bad about living in New York, where I'll never have a chance to actually buy a home. So I chose really this particular data set because I think it's easy for us to reason about, right? And I think this technique can be used especially in settings where you're using tabular data in order to make predictions, specifically for classification, single or multi-class. And a lot of us, I think, work with tabular data, and a lot of us do sort of classification tasks. And so I think it can extend all of those pipelines. Cool. Awesome. Thank you.